In this lecture, I would like to talk about the formation of the Moon. Let's start by looking at some basic properties of the Earth and the Moon. In this diagram, the sizes are to scale, but the distance between the Earth and the Moon is not to scale. Notice that you could fit about 4 moons across the Earth. Also notice that the Earth is significantly more dense than the Moon. For reference, water has a density of about 1 gram per cubic centimeter, while rock is typically about 3 grams per cubic centimeter. The density of iron is about 8 grams per cubic centimeter. So from this we can see that the Moon is likely made of material that is rock-like, but the Earth has a lot more metals like iron. Let's take a look at some of the ideas that have been proposed over the years. This model, called the capture model, proposed that the Moon formed somewhere else in the solar system and then got captured by the Earth when it wandered too close to it. Shown is a paper that discussed this idea in 1963. This idea has fallen out of favor because it's difficult in terms of orbital mechanics to get a Moon mass object to get gravitationally caught into orbit by the Earth. Something interesting to consider is that the formation mechanism of the Moon was still being debated as the Apollo program was going on in the 1960s. Next, let's look at the Co-Accretion Model. Planets formed from the accumulation and impact of material in the early solar system. Depicted on the left is an artist rendering of the accretion disk similar to the one around the Sun very early on, about 4.5 billion years ago. The co-accretion idea proposed that the Earth and the Moon just happened to have formed next to each other. I've included a paper from 1966 that supports this idea, however this model leaves a few unanswered questions. If the Earth and the Moon formed next to each other from essentially the same material, then why is the Moon significantly less dense than the Earth? Also, this model is not able to explain the rather unique angular momentum of the Earth-Moon system. We'll look at angular momentum in a moment. Another idea was proposed by George Darwin, the son of Charles Darwin. In the Fission Model, the Moon is thought to have flung off the Earth as the Earth was spinning very fast in the past. The very high spin rate of the Earth, which equates to the Earth's day being about 3 hours instead of 24 hours, is something that makes many question this idea. Was it feasible that the Earth was spinning that fast? Perhaps unlikely. Interestingly, people proposed that the seemingly missing land in the Pacific Ocean was due to that material being flung off to form the Moon. I'm showing a section of a paper from 1907 which links the Pacific Ocean to Moon formation. One of the properties of the Earth-Moon system that is often discussed is the system's angular momentum. It is often stated that the angular momentum of the Earth-Moon system is high. Here is the total angular momentum of each planetary system in our solar system. The total angular momentum shown here includes the angular momentum due to the spin of the planet, the angular momentum due to the spin of up to 4 of its most massive moons, and the angular momentum due to the orbits of those moons. You will notice that while the Earth system has the most angular momentum among the terrestrial or inner planets, the Earth system has less angular momentum than each of the outer planets. If you separate out the angular momentum due to the spin of the planet from the angular momentum due to the moons, then you'll notice something interesting about the Earth system. Notice that unlike the other planets, in the case of the Earth system, most of the angular momentum of the system is in the Moon's spin and orbit. This is likely due to the formation process of the Moon. Let's look at another property of the Moon. This figure shows the Moon's volatile element content relative to the Earth. Just by looking at the ratios, you'll notice that the Moon has relatively less volatile material than the Earth. Also, there's a trend among elements as a function of their condensation temperature. Elements with lower condensation temperatures such as thallium, bromine, cadmium, zinc, and bismuth are almost completely absent on the Moon. Elements with slightly higher condensation temperatures such as cesium, rubidium, and potassium are present on the Moon, but only about a quarter of the levels of Earth. By looking at these types of element abundances as a function of condensation temperature, we can see that the Moon has been heated to a fairly high temperature in the past. This explains the deficiency of volatiles on the Moon as compared to the Earth. Another clue to the formation mechanism of the Moon came from samples brought back by the Apollo astronauts. In this video, you'll hear or can read below the excitement of astronauts Dave Scott and Jim Irwin as they found a particular rock during the Apollo 15 mission.
Some very outstanding gray clast and white clast, and oh boy, it's a beaut, and we're going to get a hold of that one in a minute. Okay, I have my pictures, Dave. Okay, let's see, what do you think the best way to sample it would be? I think partly, could we break off a piece of the clod underneath it? Or I guess you could probably lift that top fragment right off. Yeah, let me try. sure can. And it's a white class. And it's about... Oh, man, look at that. Look at the glint. Almost see twinning in there. Guess what we just found? Guess what we just found? I think we found what we came for. Crystal and rock, huh? Yes, sir. You better believe it.
Yep, sir.
Pledge in there. Almost all pledge. She likes it. As a matter of fact, oh boy, I think we might have ourselves something close to an orthosite. Because it's crystalline in there, just a bunch of just almost all pledge. What a beaut.
The rock they were so excited to find is colloquially called the Genesis rock, since it was thought to be a piece of the original crust of the moon. One reason why this rock is unique is that it's basically made out of one mineral, that is to say plagioclase. If you picked up a rock outside, that rock will likely be made of a number of minerals. Rocks like the one from Apollo 15 are called anorthositic rocks, and finding them on the moon led scientists to propose that a large part of the moon was molten rock in the past. Cooling of that lunar magma ocean resulted in the formation of these unique rocks on the moon. So far, we've talked about 4 constraints that can help us figure out how the moon formed. We talked about how most of the angular momentum of the Earth-Moon system is due to the moon. We saw how the moon has less volatiles than the Earth, and how the moon is significantly less dense than the Earth. We also talked about how finding anorthositic rocks on the moon led to the idea that a large portion of the moon was molten rock in the past. A model that is consistent with those 4 clues is the standard or Canonical giant impact model. In this model, the early Earth is impacted by a Mars-sized object, often referred to as Theia. That giant impact would then produce a lot of hot debris and put it into orbit around the Earth. Some of that debris would then accrete to form the moon. This model is consistent with 1. Most of the angular momentum of the Earth-Moon system being in the moon's spin and orbit. 2. The moon having formed very hot, thus having a lunar magma ocean. 3. The moon having less volatile material. 4. The moon having a lower density than the Earth, since the denser material of Theia would have fallen into the Earth's interior. The figure on the right shows an edge-on view of the disk. Colors are temperatures in Kelvin. These models are typically done using a technique called smoothed particle hydrodynamics, or SPH. This is a more recent SPH simulation of the canonical giant impact model, with the colors quantifying entropy. Recent work has shown that there is a 5th clue that we need to add to our list when considering the moon's formation mechanism. It turns out that the ratio of isotopes of a number of elements, including titanium shown in this figure, are very similar between Earth rocks and moon rocks. In the canonical giant impact model, the moon forms mostly from material that was part of Theia. As such, we would expect the isotope ratios to be somewhat different between the Earth and the moon, much like there is a difference between the Earth and certain meteorites as shown in the figure. This led to newer giant impact models that can form the moon with its isotope ratios being very similar to the Earth. Let's take a look at several of the newer giant impact models. Please note that the comprehensive list of all the newer giant impact models is probably closer to 10 models since about 2011. One of the newer models suggests that they have struck the Earth in a hit-and-run manner. The advantage of this model is that the debris generated from the giant impact is mainly from the early Earth itself. As such, it naturally produces the moon that has a similar isotopic composition as the Earth. Another newer giant impact model has 2 equal mass objects, each having 50% of the mass of the Earth, colliding with each other. Like the hit-and-run model, this model produces the Earth and the moon with similar isotopic compositions. This model involves a very fast spinning Earth prior to the giant impact. Note that the Earth is spinning around itself every 2 hours. This may remind you of the fission model from earlier with a 3-hour spin rate. Another model suggests that instead of one impact, there were multiple impacts that struck the Earth to produce the moon we see today. Again, this model tries to produce a moon that has a similar isotopic composition as the Earth. Recent work modeled a structure they call Synestia, which they believe encompassed the space around the early Earth after a giant impact. Lastly, let's consider the terrestrial magma ocean model, where the impact occurs early when the Earth itself had a magma ocean. Again, the main idea is to produce a debris disk that is isotopically similar to the Earth. So how did the moon form? What we can say as of today say is that it was likely a giant impact, but the details of that impact still needs to be worked out. Let's check back in 2029. I would like to briefly discuss timing of the moon formation event. One of the ways to measure time in the early solar system is to look at hafnium and tungsten ratios. Hafnium-182 is an isotope of hafnium that undergoes radioactive decay and becomes tungsten-182, an isotope of tungsten. The half-life of this reaction is about 9 million years. Interestingly, hafnium is lithophilic, meaning rock-loving, but tungsten is hydrophilic, meaning iron-loving. Think about a primordial planet that has not undergone differentiation, meaning that the planet's interior is not separated into layers with the most dense layers being at the center. If differentiation happened later in the planet's life, then hafnium-182 would have decayed to tungsten-182, and when differentiation happened, tungsten-182 would have gone into the core with iron. On the other hand, if differentiation happened very early, hafnium-182 would have stayed in the outer layers of the planet. Then, when hafnium-182 decayed to tungsten-182, there would have been a significant amount of tungsten in the mantle of the planet. As such, by looking at the ratios of these isotopes, we can try to figure out when the planet formed, technically when the core of the planet formed. Let's take a look at the timeline of important early lunar events. The age of the solar system is estimated by the oldest calcium-aluminum-rich inclusion, CAI, shown by the dashed black line. The moon is thought to have formed between 52 to 152 million years after the beginning of the solar system. Thus, the earliest and latest moon formation times are shown in blue and orange lines respectively. There are other aspects of this figure that I would like to discuss, but I'll do that next time.